is big evolution, right? So the same principles apply as microevolution, but this time we're saying that there's bigger changes, right? Bigger changes. And we're going to talk about that today. But before we can do that, let's talk a little bit about some key terms, because this is a little bit of a controversial topic for some people. The reason it's controversial is we don't all believe the same things, and that's okay. It's part of being an American to have your own individual beliefs, and to be able to exercise and live your life based in those beliefs, right? So it's okay to have differences in beliefs, and but the reality is that the differences in beliefs will determine what you're willing to accept as true or not, right? That's just the reality. So let's make sure we define our terms, make sure that we're crystal clear on what we're talking about. If something's a belief, we're going to call it a belief. If it's a fact, we're going to call it a fact. And we'll let you guys sort through this. This is an important topic to wrestle with, I always think. It's something I've read a lot about, thought a lot about over the years. And I would encourage you, if you have questions, please ask. I'd be happy to answer those questions. Or maybe you feel more comfortable talking to your parents about this topic, or a youth pastor or somebody else. That's totally good too. All right, so key terms. A couple of key terms that we need to be aware of. First one is observations. An observation is something that we see, right? And so a lot of what we're going to be talking about today is not something that we can observe directly, right? So a lot of what we're going to be looking at when we talk about macroevolution is because this happened in the past, we're going to be looking at things that we consider evidence. It's a different kind of observation, right? Like I can see Samantha right there. I can observe Samantha right now because we're in real time with each other, right? But I can't observe Samantha yesterday, right? Even though I'm sure she was, well, no, we didn't have class yesterday. Anyway, I'm sure she was around yesterday, right? But because it's in the past, I can't see her anymore, right? But I could look for evidence of Samantha, right? I could check the attendance record and see, she was marked present for that day, right? Maybe I could check in with her teachers. That's evidence that she was here. I could see her grades, right? And say, she submitted work. That's evidence that she was here, okay? So observation, right? In science, we like to observe. We like to see stuff. But when we think about things in the past, it's not so easy. So we have to look at evidence. It's what we call historical evidence. And you guys know, just like in a trial or a court case, right, evidence is open to interpretation, or what we call inference. So let's go to the second word, inference. Inference is our second word, okay? And this is referring to what something means, right? We can both agree that Samantha was here yesterday if the attendance record says that she was here yesterday, right? What does that mean? Does it mean that Samantha was virtually here, or that Samantha was physically here, right? Or does it mean that Samantha was having a good day or a bad day, right? There's a lot of room for interpretation about what it means that Samantha was here yesterday, right? And so this is where things might be different for some people, because some people have beliefs that are going to allow them to accept some things or not accept something. And so these belief systems are important, right? Belief is an important part of life. And so what are our beliefs based on? They're principles. Principles are fundamental truths that determine what we will accept as truth. Okay, so maybe we can underline determines truth. And your principles, I hope you have principles, right? Your principles are given to you by your family. They're part of your mind. They're part of your spirit, if you will, right? It's part of who you are as a person to have these beliefs. And so those are your principles. Not a bad thing at all. But your principles will affect what you're going to accept as truth. Okay? So a couple key terms here. Observations, things that we see. Inferences, what something means that we saw. And those inferences are going to be affected by principles. All right, let's get outside of ourselves and start talking about science here again. when we talk about science, there are laws and there are theories. And laws and theories are two totally different things. Laws and theories are two totally different things. There's a misconception out there that theories are where you start, and eventually theories become laws once they're accepted, right? That's not how it works at all, okay? They do totally different things. A law is all about what, whereas a theory is all about why, okay? So to give you an illustration here, the Pittsburgh Penguins are a hockey team. Let's say that they get really good. They get really, really good, and they win every game and the Stanley Cup. Does that mean that someday they're going to be the Steelers? No, right? It's two totally different domains, right? What it takes to be good at hockey is not what it takes to be good at football, right? And so just like that, a theory is something that is never going to be a law. Laws are what we see, and to be honest, laws are kind of boring, right? Law of gravity, things fall to the earth, right? Laws of thermodynamics, right? Things tend to a random state. Theories are where science gets interesting, because this is where we try to understand why a law is occurring. And so theories are constantly being tested. They can't be proven correct. That means that we can only falsify theories, and they never become laws. Theories never become laws because they're just totally different sports. Last idea here, and that is hypothesis. A hypothesis is a low theory, and it's basically a prediction that's based on a theory. Okay? And so maybe you've heard it called an educated guess, right? It's not just a guess, it's based in a theory, but it's a way for us to test a theory in a specific setting. And so if our hypothesis is not correct, that's usually when scientists get excited, because that means there's some new information to be learned about that theory. Okay? So theories are fluid. Theories are constantly changing. The theory of evolution is never going to go away. It's just going to get more accurate, right? That's the idea, is that it's something that's going to only get better as we continue to test our hypotheses, okay? Okay, so all that to say, let's talk a little bit about micro and macroevolution, okay? Microevolution is on the left, macroevolution is on the right, and these bullets are set up as contrasting points. So the first bullet on the left is meant to be compared to the first bullet on the right, okay? So let's underline a couple more key terms here. First one is microevolution means small genetic changes in a gene pool, and macroevolution means big genetic changes in a gene pool. Small and big, micro and macro. Okay. So hope you underline small and big. Okay. And so what do we mean when we say small and big, right? Those are kind of squishy terms. Well, here's a more precise way to say it, okay? Microevolution is change within a species. Okay, so if let's say a dog is evolving, right? Okay, a population of dogs are evolving. They're a great example of microevolution, right? We believe that we're pretty sure that dogs are essentially wolves. If you look at the DNA of a dog, even a sweet dog like Cookie is essentially genetically a wolf, right? But of course, dogs are very different than wolves, but they're still technically part of the same species, right? So a change within a species, that's microevolution. Macroevolution is a large change, we said. What we mean by that is we're going to get new species. When we talk about macroevolution, we're talking about change that causes a brand new species. That would be like a group of dogs becoming something other than dogs. Right? It wouldn't necessarily be them becoming apes or cats or something else, because those things already exist. It might be something totally new on the planet that's never existed before. That's the kind of change that we're talking about with macroevolution. Microevolution is short term. That means it happens all the time. It doesn't take millions of years for us to think about microevolution. Macroevolution is a long-term process. And if we want to, let's add in how long? millions of years. So this is one of the hang-ups for people when we talk about this topic is we can't directly observe macroevolution. We can't directly observe it, then how do we know that it occurred, right? And these are things that you have to wrestle with, right? These things you have to think for yourself about, okay? But it would definitely require a bigger period of time for it to work, whereas microevolution is something that we're seeing happening all the time, all around us. Microevolution, we said there were 3 ways that it can happen, right? Genetic drift, gene flow, and natural selection, right? Maybe we could even number them. Let's number them. 1, 2, 3 ways, right? And none of those are controversial. Basically, they say that animals die, animals reproduce, and animals migrate, right? And so those 3 things are enough to cause microevolutionary changes. Okay, here's the big one. I put this one in bold because this one is the most important, right? This is the biggest one. Macroevolution requires something that microevolution doesn't require, and that is positive random mutations. You guys remember mutations are changes in our DNA, right? Changes in our DNA are mutations. And you'll notice that I didn't just say any old mutations, right? In order for it to be part of macroevolution, these mutations would have to be positive and random. Okay, so positive mutations. If you remember back when we talked about mutations a couple of weeks ago, most mutations we said are bad, right? They cause things like cancer. They cause things that make us sick or make us unable to reproduce or unable to compete, right? Those are bad mutations, and that's most of the mutations that we're observing. What this requires, macroevolution requires, is positive mutations that would make an organism better able to reproduce would be positive, or better able to camouflage, or better able to live its life, right? And so we said that's extremely rare, right? But hypothetically possible. This is where most of the controversy comes from, is what's possible with things that are so unlikely to occur. And so some people believe that that's absolutely what happened, right? They believe that unlikely things happened enough times over millions of years to cause positive random changes and make all of the different species on the planet. Whereas other people say, look, it's not likely, even with a long period of time, it's still not likely. And so, again, that's where there's going to be differences based on what your principles will allow you to accept as true. Okay? Any questions about that? Let's put a little star next to that one. I put it in bold, right? That's really the crux of the issue, right? That's really what causes the controversy is what can positive random mutations do? Okay? That's really where all the controversy comes from, and how much time would be required, and what would be the mechanism for that to occur. And of course, it's complicated by the fact that we can't see any of this happening in real time, and it's something that we had to rely on historical evidence to make determinations about. Okay, let's see. Another item here, this one's meant to correlate here as well, is isolation. Requires isolation, and that means separation.
Yeah, and when doing, remember in math that when doing slope.
Say that again?
When doing slope during math class,
okay,
it needs to be in slope intercept form, and y is by itself.
Okay. So here's a little illustration of what we're talking about here. When we say isolation, right? Maybe when you were a little kid, your mom and dad put you in timeout and isolate you, right? The idea is that you're separate and you're thinking about the bad thing that you did, right? And hopefully developing remorse, sadness for your poor choices. Anyway, that's isolation. Isolation in a genetic setting means that one gene pool is going to become two gene pools. And so what's going to separate one gene pool into two gene pools? Well, it's either going to be positive random mutations, or it's going to be something physically that separates them. And so maybe what we could say, and I'm using GP for gene pools. Maybe I'll put that in parentheses here, GP for gene pools, okay? Separation of gene pools. There's really two things that can separate a gene pool. They can actually be sexually separated. That means even though they're living next to each other in the same place, a mutation has caused them to not be able to reproduce with each other. Or it could happen that they are geographically isolated. And so what that means is they live in different places. And because they live in different places, what it takes to be successful at survival in one place might be different than another place. Okay, and so this is why we think we're seeing all of these unusual species living on islands, right? Because they're isolated from the rest of the world. There's species on Australia that don't exist anywhere else on the world. Madagascar is another great example of an island that is isolated. So the organisms there have evolved differently as a result. Okay, last little bit here, guys. Thanks for being so patient. Can be seen, right? We can observe that. Maybe we should be observed, right? But when we talk about macroevolution, it cannot be seen. And because mutations are random, that means it also cannot be tested, right? In science, we don't do random, right? What kinds of experiments do we do? Just random experiments? No, we do controlled experiments. We try to eliminate randomness, right? And as soon as we create an experiment, it's no longer random or no longer natural. And so it's really impossible for us to set up an experiment to see what kinds of positive random mutations could impact a population. Go ahead. Yeah. Okay.
Well, you gotta take a screenshot.
You're gonna take a screenshot of that. Okay, good idea. How much of the screen do you need?
Just that much now then.
Just this part?
Yeah.
Okay.
Actually, go up a little bit. I'll get that too.
You're gonna get that too. That's mostly just underlining.
All right, there, got it.
Okay. You got that? Okay. Do you guys have any questions? Hopefully I haven't offended anybody. Hopefully I've been able to make you think a little bit about the topic. Let's just go on to two more things. I just want to unpack positive random mutations a little bit and isolation a little bit, because that's really what makes macroevolution different than microevolution. So when we say positive random mutations, we mean rare mistakes when copying the DNA. That's when mutations most commonly occur. They can also happen as a result of environmental factors. When we say that they're positive, we don't mean they're a charge. We mean that they have a new phenotype that we call an adaptation. And it makes the organism better able to survive. So it has to result in a new trait or a new adaptation that makes the organism better to survive. This is extremely rare. It must occur in a sex cell to affect a gene pool. So it wouldn't be part of the reason this is very rare, right? If I get a mutation in my skin cell and it gives me a new pigmentation that allows me to camouflage, that's great, but my kids aren't going to benefit from that unless that mutation is in a sex cell. Because remember, it's only the genes in your sex cells that get passed on to the next generation. And then random. What do we mean by random? We mean without a predictable cause. But that basically, it's like saying without cause. But that's not what we mean, right? Because without cause wouldn't make any sense at all. But without a single consistent cause is basically the idea of random. So what causes a mutation at one moment is totally different for another. And so as a result of random, right, we can't test these kinds of changes. Isolation anything that prevents some individuals from mating. So let's underline prevents mating. Okay, we can isolate individuals in a gene pool by preventing them from mating. And this spot allows for divergent evolution, which is basically what I tried to diagram here. It's the idea that one gene pool gets divided into two gene pools, and that these two gene pools can no longer mate with each other. And so that means what happens in that top gene pool is not going to be shared with what's happening in the bottom gene pool. So this allows the gene pools to become more different. So allows two populations, let's say allows to become different. And we said there's two ways that isolation can happen. They can happen ecologically, where there's no mating because they are in two different places. So ecological, I think I called it geographical before. I guess Keystones uses the term ecological. Ecological isolation, they are in different places and so they can't mate. And then reproductive isolation, they don't mate because their genes are different. So maybe there's a change in their mating ritual, or maybe there's a mating season change, and as a result, they just don't mate. You want to screenshot that, Brandon?
Yeah.
Okay. All right. Almost done. Just a couple of diagrams on the second page here that I'd like you to be okay with. Let's just look at the second page. Here's an idea or example. Did I go too fast? Sorry. All good? Cool. All right, guys. Two little images to hopefully illustrate what we're talking about. In this first image, we've got, this is meant to be time, okay? This is as time goes on, right? So we're starting with an ancestral bunny rabbit, okay? So maybe this guy here is an ancient bunny rabbit, okay? And it looks like the population of bunny rabbits got separated by this river. What kind of isolation would that represent? We have two populations or two gene pools of bunny rabbits separated by a river. These bunny rabbits can't swim across the river. So the bunny rabbits over here on this side are only mating with other bunny rabbits on that side. And the bunny rabbits on this side, on the right side, are only mating with bunny rabbits on the right side. And so they can become different from each other. What kind of isolation would that be? Ecological or reproductive? Ecological. Good. And so maybe in the middle here where the river is, let's write the word ecological. There's something physically separating them. And so the population on the left is continuing to be like their ancestor, but the population on the right, maybe they live in a different set of conditions. So what it takes to be successful at survival on the right is different, and so they're becoming more different. That's called divergence. The way that we would represent that kind of change is through what's called a phylogenetic tree. That's what this is showing, a phylogenetic tree. Phylogenetic tree. And the idea here in a phylogenetic tree, again, I guess the time arrow is going to be going the opposite direction of this illustration. So time is here. But as time goes on, these lines represent gene pools. And so each spot where you see a Y in the illustration is a moment in history where isolation occurred. Okay, so these Ys, these spots where the two lines diverge, okay, are moments where two gene pools became isolated from each other. Okay? And so the nice thing about a phylogenetic tree is you can make comparisons about how related or how recently two gene pools diverged. If you look at individual A and B diverged more recently in time than, say, individual A and H. A and H diverged much more anciently in time. And so we would expect that individuals A and B should have some of the same traits or some of the same adaptations, whereas individuals A and H should be very different. And so this is the idea of a phylogenetic tree. All right, that's everything, guys. Thanks so much for bearing with me.